Imagine staring at a photograph of the universe taken just moments after its birth. Not an artist's rendering, not a scientist's guess, but actual light, older than the first stars, older than the galaxies themselves. This is the cosmic microwave background, the oldest light in existence, a ghostly whisper from the very dawn of time. It's a snapshot frozen in space, a relic from when the universe was a seething, newborn sea of energy, barely 400,000 years old. And yet, this ancient glow, this fossil of the Big Bang, holds secrets that defy explanation. Scientists have spent decades mapping its subtle ripples, its faint temperature variations, only to uncover mysteries that challenge everything we think we know about the cosmos. Picture the cosmic microwave background as a cosmic fingerprint, a pattern etched into the fabric of space itself. At first glance, it appears uniform, a quiet afterglow of creation. But look closer, and the anomalies emerge, regions inexplicably hotter or colder than they should be, strange alignments that seem to defy chance, vast voids where the universe feels eerily empty. These aren't just quirks, they're cosmic conundrums that have baffled the brightest minds in astrophysics. Why does the universe have a cold spot so large it shouldn't exist? Why do some parts of the sky seem to align in ways that hint at something beyond our current understanding? The more we learn, the clearer it becomes. The cosmic microwave background is not just a window into the past, it's a puzzle box waiting to be opened. Today, we're diving into 25 of the most profound mysteries hidden within this ancient light. From the curious axis nicknamed the axis of evil to the tantalizing hints of alternate universes, each clue we uncover leads to deeper questions. What if the anomalies in the cosmic microwave background are evidence of a universe before the Big Bang? Could they point to dimensions beyond our own? Or are we simply seeing the limits of our own understanding? This journey isn't just about science, it's about standing at the edge of the known and peering into the unknown. So let's unravel these enigmas together, piece by piece, and discover why the oldest light in the universe might just hold the keys to the greatest secrets of all. One of the most baffling secrets hidden within the cosmic microwave background is known as the horizon problem. Imagine looking at 2 points in the sky separated by billions of light years, so far apart that light from one could never have reached the other since the beginning of time. And yet, when we measure their temperatures in the CMB, they're almost identical, matching to within a tiny fraction of a degree. This shouldn't be possible. If the universe started as a searing, chaotic fireball, how could regions that never had time to exchange heat or information somehow settle into perfect equilibrium? According to the laws of physics as we know them, this level of uniformity breaks the rules because nothing, not even light, could have traveled fast enough to even out these temperatures in the brief time the universe existed before the CMB was emitted. This cosmic conundrum led scientists to propose a radical fix: cosmic inflation. The idea is that in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light itself, stretching a microscopic patch of space into something vast and uniform in an instant. Inflation would explain the eerie symmetry of the CMB, smoothing out the early universe like a balloon inflating to erase its wrinkles. But while inflation has become the leading explanation, it's not without its own puzzles. For one, we've never directly observed the particle or field that would have driven this hyper-expansion. Some researchers argue it's a cosmic band-aid, a clever idea that fits the data but feels more like a mathematical fix than a proven truth. Alternative theories have emerged, each with its own twist. Maybe the speed of light wasn't constant in the early universe, allowing distant regions to communicate. Or perhaps the universe is far older than we think, giving it more time to even out. Some even suggest our cosmos is just one bubble in an endless multiverse, where collisions between neighboring universes left subtle marks. The horizon problem forces us to confront a humbling truth. The cosmic microwave background, for all its revelations, still guards mysteries that might require rewriting physics itself. And that's just the first of its enigmas. Hidden within the cosmic microwave background lies a region so bizarre it's been nicknamed the cold spot, an area chillingly colder than its surroundings by a margin that defies conventional explanation. Stretching nearly 2 billion light-years across, this cosmic anomaly isn't just a statistical fluke. It's a gaping hole in our understanding of the universe's structure. One leading theory suggests the cold spot might be a supervoid, an unimaginably vast emptiness where galaxies are eerily scarce. In such a void, light from the CMB would lose energy as it traverses the expanding space, a phenomenon called the integrated Sachs-Wolf effect, potentially explaining the temperature drop. The problem: the largest known voids we've mapped are still too small by a factor of 10 to account for the cold spot's extreme chill. If it is a void, it's unlike anything else in the observable universe, a cosmic ghost town on a scale that shouldn't exist. Then there's the far more radical idea: the cold spot could be a bruise from a collision with another universe. In the multiverse scenario, our cosmos might have bumped into a neighboring bubble universe during inflation, leaving behind a telltale imprint in the CMB. While mathematically intriguing, this theory dances on the edge of testability. How do you prove an encounter with a universe forever beyond our observational reach? Some physicists dismiss it as speculation, while others argue it's the only hypothesis bold enough to match the anomaly's strangeness. Skeptics propose a simpler answer: maybe the cold spot isn't real at all. Could it just be an artifact of instrumental noise or an unlucky statistical fluctuation? Detailed observations from missions like Planck have largely ruled out measurement errors, and the odds of such a fluctuation occurring naturally are astronomically low, roughly 1 in 50,000. The cold spot refuses to vanish under scrutiny, leaving scientists with a dilemma: accept an unprecedented cosmic structure, embrace a multiverse smash-up, or admit a fundamental gap in our physics. What makes the cold spot so captivating isn't just its existence, it's the way it forces us to question the limits of our cosmic maps. Whether a void, a multiverse relic, or something even stranger, this icy enigma reminds us that the universe still holds surprises no theory has yet tamed. And as we'll see, it's just one of many cosmic whispers challenging us to listen more closely. The cosmic microwave background holds another enigma so unsettling that scientists gave it a name straight out of a cosmic thriller: the axis of evil. At first glance, it sounds like something from science fiction, but the reality is even stranger. When researchers mapped the subtle temperature variations in the CMB, they expected randomness, a universe without favoritism, where hot and cold spots scattered like spilled marbles. Instead, they found something that sent a ripple through cosmology. These fluctuations weren't entirely random. They appeared to align along a particular axis, as if the universe itself had whispered a secret direction. This discovery flies in the face of one of cosmology's bedrock principles, the cosmological principle, which states that the universe should look roughly the same in every direction, with no preferred location or orientation. Yet here we are, staring at data that seems to contradict this fundamental idea. Some researchers argue this alignment is just a statistical fluke, a cosmic illusion born from the way we process the data or the limitations of our observations. After all, when you're mapping something as subtle as the CMB, even tiny errors or biases could create phantom patterns, but others aren't so quick to dismiss it. What if the axis of evil is real? What if the universe truly does have a preferred direction, a hidden structure written into its oldest light? The implications would be staggering. It could mean our understanding of the Big Bang is incomplete, that the early universe wasn't as uniform as we thought. Some theories suggest exotic physics, like the influence of a neighboring universe or a space-time structure far more complex than our models predict. Others propose that the axis might be a relic of pre-Big Bang dynamics, a shadow of some primordial process we've yet to uncover. The debate is far from settled. Every new analysis of the CMB data brings fresh arguments. Skeptics point out that later observations, like those from the Planck satellite, show weaker evidence for the axis, suggesting it might fade away with better measurements. But believers counter that the signal, though subtle, stubbornly persists, refusing to vanish entirely. Whether the axis of evil is a cosmic mirage or a genuine crack in our understanding, one thing is certain. It forces us to question whether the universe is as indifferent and uniform as we once believed. And in that uncertainty lies the thrill of discovery, the chance that even our deepest assumptions might one day be upended. If the cosmic microwave background is the universe's baby picture, then the structures we see in it today, galaxies, clusters, and vast cosmic webs, should match the faint imprints left by those early density fluctuations. But here's the puzzling part. When scientists compare the CMB's subtle ripples to the large-scale structures we observe in the modern universe, something doesn't add up. The universe seems to be missing its giants. Simulations based on our best models of dark matter and gravity predict an abundance of enormous galaxy clusters and sprawling superstructures, yet the real cosmos appears curiously short on these colossal formations. It's as if the universe forgot to build some of its biggest skyscrapers. This discrepancy points to one of two possibilities. Either we're misunderstanding how dark matter sculpts the cosmos, or our grasp of gravity itself is incomplete. Dark matter, that invisible scaffolding thought to hold galaxies together, should have clumped under its own gravity over billions of years, creating dense hubs where galaxies congregate. But if the observed structures are sparser than predicted, perhaps dark matter isn't as sticky as our models assume. Some theories suggest dark matter particles might interact in unexpected ways, like bouncing off each other or decaying over time, subtly altering how structures form. Then there's the more provocative idea. What if gravity doesn't behave exactly as Einstein predicted on cosmic scales? Modified Newtonian dynamics, or MOND, proposes that gravity weakens differently over vast distances, potentially explaining why massive structures didn't coalesce as expected. While mainstream cosmology still favors dark matter, MOND gains traction whenever observations defy predictions, like this shortage of cosmic giants. But the plot thickens. Recent sky surveys have discovered a handful of ultra-large structures, like the Hercules Corona Borealis Great Wall, a filament of galaxies stretching 10 billion light-years, that seem too big to exist under current theories. If the universe is missing some giants but over-delivering others, it suggests our models are missing a critical piece of the puzzle. Whether it's quirks of dark matter, tweaks to gravity, or something entirely unforeseen, the CMB's structural whispers are forcing us to rethink how the cosmos builds its architecture. And every new map of the sky brings us closer to either solving the mystery or uncovering a deeper one. Diving deeper into the cosmic microwave background's mysteries, we encounter something that sounds straight out of quantum physics class: the quadrupole and octupole anomalies. These terms might seem intimidating, but they're simply ways to describe how the CMB's temperature variations are distributed across different scales. Think of it like studying the ripples on a pond. Some are small and frequent, while others are broad and sweeping. The quadrupole refers to patterns stretching across 60 degrees of the sky, while the octupole covers even wider angles. And here's where things get weird. These large-scale fluctuations are far weaker than our theories predict. It's as if someone turned down the volume on the universe's biggest vibrational notes, leaving cosmologists scrambling to explain the silence. One possibility is that the universe isn't infinite, at least not in the way we've always assumed. If space wraps around on itself like a cosmic hall of mirrors, finite in size but without edges, it could suppress those large angle fluctuations. Picture blowing up a balloon with a pattern on it. If the balloon is small enough, certain large designs simply can't fit. Similarly, a finite universe might be too small to accommodate the expected quadrupole and octupole variations. The idea isn't just speculative mathematically. A finite cosmos could neatly explain the missing power in these moments, but proving it is another matter. If the universe is finite, its scale would have to be staggeringly large, far beyond our observable horizon, leaving us with a tantalizing but unverifiable hint. Then there's the wilder twist. What if unknown forces or fields in the early universe actively suppressed these fluctuations? Some theorists propose exotic physics, like a brief phase of dark energy domination before inflation, which could have smoothed out the largest ripples. Others suggest primordial magnetic fields or even interactions with hidden dimensions might have played a role. These ideas push the boundaries of known physics, but the anomalies demand bold thinking. After all, when the data refuses to fit the model, sometimes the model needs reimagining. Skeptics, of course, argue that the anomalies might just be statistical quirks or artifacts of how we process the CMB data. Remove a particular foreground signal or tweak the analysis method, and the quadrupole and octupole might align better with expectations. Yet, even after accounting for these factors, the discrepancies persist. Whether it's a finite universe, new physics, or something even stranger, these anomalies remind us that the cosmos still holds cards it hasn't revealed. And with every new observation, we edge closer to understanding whether we're seeing the limits of our models or the first clues to a deeper cosmic truth. Among the cosmic microwave background's most perplexing traits is something that at first glance seems ordinary: its staggering uniformity. Across the entire sky, the temperature of this ancient light varies by less than 1 part in 100,000, a whisper-thin difference that feels almost too perfect. If the universe began as a churning cauldron of quantum randomness, as most theories suggest, why doesn't the CMB bear more dramatic scars from those chaotic early moments? The challenge lies in the math. Quantum fluctuations in the infant universe should have left behind a tapestry of wildly uneven hot and cold spots, regions where density varied dramatically due to the inherent unpredictability of particle behavior at microscopic scales. Instead, the CMB presents a cosmic calm, a near symmetry so precise it feels orchestrated. It's like expecting the aftermath of an explosion to show jagged debris scattered in all directions, only to find the pieces arranged in eerily uniform rows. One radical explanation gaining traction is the multiverse theory. Imagine our universe as one bubble in an endless froth of cosmic foam, each bubble with its own unique physics. In this scenario, the uniformity of our CMB might not be a coincidence but a selection effect. Only in universes where conditions were finely tuned, where inflation stretched quantum wrinkles into near smoothness, could structures like galaxies, stars, and eventually life arise. In other words, we might live in a universe that appears improbably uniform simply because we couldn't exist in the more chaotic ones. But the multiverse isn't the only contender. Some physicists propose that unknown fundamental laws govern the early universe, acting as a cosmic iron to smooth out wrinkles before they could imprint on the CMB. Others speculate that the universe underwent a phase of thermalization far more efficient than current models predict, effectively erasing asymmetry before the first light was emitted. There's even the controversial idea that the universe's uniformity hints at a cyclical cosmology, where the Big Bang was preceded by a previous cosmic epoch that pre-smoothed the playing field. Skeptics, however, argue that the apparent uniformity might reflect gaps in our observational reach. Just as a mountain range seems flat when viewed from a great enough distance, perhaps the CMB's smoothness is an illusion of scale, a trick of perspective that finer measurements could disrupt. Yet every new dataset, from Planck to future observatories like the proposed CMB Stage 4 experiments, seems to reinforce the mystery rather than resolve it. What makes this enigma so profound isn't just the scientific challenge, it's the philosophical weight. If the multiverse explanation holds, it suggests a cosmos teeming with unseen realities, each governed by different rules. If another theory prevails, it could rewrite our understanding of quantum beginnings. Either way, the CMB's quiet uniformity speaks volumes. The universe's oldest light might be hiding its loudest secrets in plain sight. Beneath the cosmic microwave background's serene glow lies a phenomenon so unsettling it defies conventional cosmology: the dark flow. Across billions of light years, hundreds of galaxy clusters are caught in a silent but relentless current, all streaming toward a single, unseen point beyond the edge of our observable universe. It's as if the cosmos itself is being tugged by something vast and invisible, something that shouldn't exist. This motion isn't just subtle drift, it's a coordinated movement at staggering speeds, up to 1,000 kilometers per second, far faster than the expansion of space alone could explain. When scientists first detected this flow in the early 2000s, skepticism ran high. Could it be an artifact of incomplete data or measurement errors? Yet repeated studies, including analyses of X-ray clusters and the CMB's kinetic Sunyaev-Zeldovich effect, only sharpened the mystery. The dark flow persists, stretching over distances so immense that no known force in our universe should have the reach or power to orchestrate it. The most tantalizing explanation: the pull might originate from something beyond our cosmic horizon, a massive structure or gravitational anomaly lurking in the unobservable darkness. One provocative theory suggests it's the gravitational imprint of another universe, a neighboring bubble in the multiverse foam, exerting influence across the dimensional divide. In this scenario, the dark flow would be a cosmic wake, evidence that our universe isn't alone but tethered to something immense and alien. Others propose less exotic but equally mind-bending alternatives. Perhaps the early universe's inflation wasn't perfectly uniform, leaving behind density variations so colossal they warp spacetime on scales we've yet to map. Or maybe our understanding of gravity itself breaks down over these vast distances, hinting at modifications to Einstein's relativity. Even the cosmological principle, the idea that the universe is broadly homogeneous, comes into question. If the dark flow is real, it suggests a cosmos far more asymmetrical than we ever imagined. Critics counter that the flow could still be an illusion, a statistical fluke amplified by selective data interpretation. But the consistency of observations across different methods keeps the debate alive. Whether it's a multiverse tug of war, a flaw in our physics, or something beyond current theory, the dark flow forces us to confront a humbling truth. The universe's oldest light might be pointing us toward mysteries we're only beginning to glimpse, and some answers may lie forever out of reach. One of the cosmic microwave background's most subtle yet persistent anomalies revolves around something called the dipole, a faint temperature variation across the sky caused by Earth's motion through space. As our planet hurtles through the cosmos at roughly 600 kilometers per second, it creates a Doppler effect in the CMB, making one half of the sky appear slightly warmer and the other slightly cooler. This isn't just expected, it's foundational, a cosmic speedometer built into the oldest light. But here's the catch: when scientists compare this dipole to other independent measurements of our motion, like the way distant galaxies appear to stream in one direction, the numbers don't quite match. The CMB's dipole suggests we're moving faster than these other cosmic yardsticks imply, as if part of our velocity comes from somewhere we can't see. The discrepancy isn't enormous, just a few percent, but in cosmology, even tiny mismatches can signal something profound. One possibility is that our measurements are being thrown off by local influences, like the gravitational pull of the Milky Way's nearest cosmic neighbors. The Great Attractor, a massive concentration of galaxies in the direction of the constellation Centaurus, tugs on us with undeniable force. Yet even accounting for its influence, the math still leaves a gap. Could there be even larger, unseen structures beyond our current maps, their gravity nudging us in ways we haven't detected? Some theorists speculate about superclusters or dark matter filaments so vast they stretch beyond our observational horizon, their cumulative pull adding to the mystery. Then there's the more unsettling idea. What if the dipole anomaly isn't about unseen mass at all, but a flaw in our assumptions about the CMB itself? If the early universe wasn't perfectly uniform, if inflation left behind ripples on scales larger than we've measured, those primordial wrinkles could be imprinting a false signal on the dipole. Imagine trying to measure the wake of a boat while standing in choppy waters. The background turbulence might distort your readings. Similarly, cosmic irregularities could be muddying the dipole's true value, making Earth's motion appear exaggerated. Skeptics argue the mismatch could simply stem from measurement uncertainties, a stacking of tiny errors across different observational methods. Aligning galaxy surveys with CMB data involves stitching together disparate datasets, each with its own margins of error. But as instruments like the James Webb Space Telescope refine our cosmic maps, the discrepancy stubbornly lingers. Whether it's hidden mass, primordial chaos, or something entirely unforeseen, the missing dipole reminds us that even the most basic cosmic measurements can harbor secrets, and that the universe's oldest light might still be misdirecting us. Beneath the cosmic microwave background's chaotic tapestry of hot and cold spots, some researchers claim to have found something even more unexpected: whispers of perfect circles etched into the ancient light. These concentric rings, faint but seemingly deliberate, have sparked a radical idea. What if the Big Bang wasn't the true beginning, but just one chapter in an endless cycle of cosmic death and rebirth? The theory, known as conformal cyclic cosmology, proposes that our universe is caught in an eternal loop. Each cycle ends with a cold, empty expanse so vast that time itself loses meaning, only to be reignited by a new Big Bang. If true, collisions between black holes in a previous iteration of reality could have sent shockwaves rippling through space-time, leaving behind circular imprints in the CMB like echoes from a forgotten age. When scientists scanned the data, they identified regions where temperature variations aligned into concentric patterns, rings within rings, as if the universe had been stamped with a cosmic fingerprint. But not everyone is convinced. Skeptics argue these circles could be statistical illusions, the result of poring over so much data that random fluctuations start to resemble patterns. After all, stare at any random noise long enough, and your brain will inevitably find shapes, a phenomenon known as pareidolia. When independent teams attempted to replicate the findings, some circles vanished under different analysis methods, while others appeared weaker or shifted position. The debate hinges on probability. Are these rings genuinely improbable or just artifacts of how we slice the cosmic pie? Then there's the challenge of alternatives. Could these circles be explained by something less exotic, like the gravitational lensing of distant galaxy clusters warping the CMB's light? Or perhaps instrumental noise in early satellite data left subtle, ring-like artifacts? Even the Planck mission's higher resolution maps haven't settled the debate, with some circles persisting while others fade into the background. What makes this mystery so compelling isn't just the boldness of the claim, it's the stakes. If these rings are real, they'd be the first tangible evidence of a universe that existed before our own, a revelation that would rewrite cosmology. But if they're mirages, they serve as a cautionary tale about how easily pattern-seeking minds can project meaning onto randomness. For now, the circles remain in limbo, too intriguing to dismiss, yet too uncertain to confirm. And in that uncertainty lies the essence of science, the relentless pursuit of truth, even when the universe refuses to hand us easy answers. When the universe was just minutes old, it wasn't stars or galaxies that first emerged from the primordial fire, it was atoms. In those blistering early moments, the cosmos acted like a nuclear fusion reactor, forging the lightest elements, hydrogen, helium, and trace amounts of lithium and beryllium. The cosmic microwave background lets us peer back to this era, not with light but through the fingerprints of these elements, their predicted abundances encoded in the CMB's temperature fluctuations. The math is elegant. Combine the known laws of nuclear physics with the conditions of the early universe, and you should be able to calculate exactly how much of each element was created. Hydrogen and helium match these predictions with stunning precision, but lithium, the universe seems to have misplaced nearly 3/4 of it. This isn't just a minor accounting error. The discrepancy, known as the lithium problem, is glaring. When astronomers measure lithium levels in the oldest stars, those that formed from nearly pristine material in the early cosmos, they find only about 1/4 of the amount predicted by Big Bang nucleosynthesis models. It's as if someone took a cosmic eraser and scrubbed away most of the universe's third lightest element. The CMB's pristine snapshot of the early universe insists the lithium should be there. So where did it go? One possibility is that our understanding of particle physics is incomplete. The calculations for Big Bang nucleosynthesis rely on precise nuclear reaction rates, how quickly protons and neutrons fused in that primordial soup. What if unknown particles or forces subtly altered these reactions? Some theorists propose that hypothetical particles like actions, or even variations in the fundamental constants of nature, could have skewed lithium production. Others suggest exotic decays of unstable particles might have siphoned off lithium or converted it into other elements. These ideas walk a fine line between innovation and desperation, invoking new physics to solve a single observational puzzle. Then there's the thornier issue. Maybe we're measuring lithium wrong. Ancient stars aren't time capsules. Over billions of years, their surfaces can churn, dredging up material from deeper layers where lithium may have been destroyed. Alternatively, diffusion could have slowly dragged lithium atoms downward, away from the stellar atmospheres we observe. But even after accounting for these processes, the shortfall persists. Some astronomers argue we're underestimating how much lithium gets destroyed in stars, while others counter that no known stellar mechanism can explain the full discrepancy. The most unsettling explanation: both the predictions and the measurements could be correct, meaning our models of the early universe are missing something fundamental. If lithium was somehow preferentially ejected from certain regions of space, or if pockets of the primordial cosmos had wildly different temperatures, it might explain the mismatch. But these scenarios require physics far outside our current playbook. The lithium problem isn't just about missing atoms, it's a test of cosmology's bedrock theories. If standard models can't account for this anomaly, it hints at gaps in our understanding of everything from nuclear reactions to stellar evolution. And until we solve it, the universe's oldest stars will keep silently protesting. The story of the elements isn't as simple as we thought. Among the cosmic microwave background's most mathematically puzzling quirks is its strange preference for symmetry specifically, a lopsided dominance of even parity patterns over odd parity ones. In simpler terms, when scientists analyze the CMB's temperature fluctuations, they find the universe seems to favor certain types of geometric arrangements, like mirror images, while suppressing others. It's as if the cosmos rolled a loaded die at the beginning of time, and we're only now noticing the bias. This oddity isn't just a footnote in cosmology. It challenges our understanding of how the universe expanded in its first moments. The leading theory, cosmic inflation, predicts that quantum fluctuations should have produced equal amounts of even and odd parity patterns, like a perfectly balanced seesaw. Yet the CMB stubbornly refuses to comply, showing a subtle but statistically significant tilt toward evenness. Some researchers argue this could mean inflation wasn't as uniform as we thought, with unknown forces or fields tipping the scales during that explosive growth spurt. Others speculate it might hint at entirely new physics, like a primordial force that acted selectively on spacetime's geometry, leaving behind this cosmic fingerprint. One provocative explanation involves gravitational waves from the early universe. These ripples in spacetime, if strong enough, could have imprinted a parity preference on the CMB. But here's the twist. Current models struggle to produce waves of the required magnitude without invoking exotic ingredients, like colliding universes or higher dimensional physics. Skeptics counter that the anomaly might be an artifact of how we filter foreground noise from CMB data, or even a quirk of our particular vantage point in the universe. After all, if we're seeing just one slice of an infinite cosmos, could statistical flukes masquerade as profound imbalances? The deeper implication is philosophical. If the universe truly has a hidden symmetry bias, it suggests the laws of physics might not be as neutral as we assumed. From the formation of galaxies to the behavior of fundamental particles, parity could play a role we've yet to grasp. Future experiments, like precision measurements of the CMB's polarization, may settle the debate, but for now, this cosmic preference remains one of the quietest yet most profound mysteries written into the oldest light. While the cosmic microwave background's temperature variations tell one story, its polarization. The way its light waves vibrate unlocks another. Imagine the CMB as not just a static image, but a tapestry of light with hidden textures woven by the universe's earliest moments. These textures come in two distinct flavors, E modes and B modes. E modes, the simpler of the two, arise from density fluctuations in the primordial plasma, like ripples on a pond frozen in time. But B modes, they're the holy grail of cosmology, twisting patterns that could carry the signature of gravitational waves from the universe's first trillionth of a second. The hunt for B modes isn't just academic, it's a direct test of cosmic inflation. According to theory, inflation's violent expansion should have sent shockwaves through spacetime itself, creating gravitational waves that left swirling imprints in the CMB's polarization. Detecting these telltale twists would be like finding the fingerprints of the Big Bang's engine. But here's the catch: B modes are vanishingly faint, buried under noise from interstellar dust, galaxies, and even the quirks of our own instruments. When scientists claimed a tentative detection in 2014, the announcement sent shockwaves through the scientific community until follow-up studies revealed the signal was likely cosmic dust masquerading as primordial glory. The absence of definitive B modes isn't just disappointing, it's puzzling. If inflation happened as modeled, why haven't we seen its gravitational wave signature? Some theorists argue we might be looking for the wrong pattern. Perhaps inflation's waves were weaker than predicted, or their signal is obscured by unknown foregrounds. Others suggest inflation didn't happen at all, pushing alternatives like bouncing cosmologies or variable speed light in the early universe. Then there's the middle ground. Maybe inflation occurred, but at energies too low to produce detectable B modes, leaving us with a quieter cosmic story than we'd hoped. What makes this mystery so gripping isn't just the scientific stakes, it's the irony. The CMB, our clearest window into the past, might be hiding its most explosive secrets in plain sight. Future telescopes like the Simon Array or SIMB S4 aim to peer deeper, but for now, the silence of the B modes echoes with unanswered questions. Whether they're waiting to be found or revealing a cosmos less chaotic than we imagined, their story is far from over. If the cosmic microwave background were a flawless symphony of primordial light, spectral distortions would be its barely audible wrong notes, subtle deviations from the perfect thermal harmony we expect. The CMB spectrum is famously a near-perfect blackbody, a thermal curve so pristine it earned Nobel Prizes. But perfection in science often hides the most tantalizing clues. Astronomers now scour this spectrum for minute anomalies, hunting for the faintest kinks or bumps that could betray universe-shaking secrets. These distortions come in two primary flavors, mu and Y. A mu-type distortion would appear as a tiny excess of energy at specific wavelengths, like a barely perceptible hum in the background noise. This could signal the decay of exotic dark matter particles in the early universe, their death throes releasing just enough energy to heat the primordial plasma. Imagine dark matter as a cosmic ice cube melting into the CMB's soup, leaving behind a faint but measurable warmth. A Y-type distortion, on the other hand, would look like a smearing of the spectrum's peak, hinting at later energy injections, perhaps from the fiery deaths of the first stars or the explosive growth of supermassive black holes. The challenge lies in the staggering precision required. Detecting these distortions is like trying to spot a single misplaced grain of sand on a beach miles long. Current instruments like the Planck satellite lack the sensitivity to catch such whispers, but next-generation observatories like the proposed PIXI mission are designed to listen. PIXI could measure the CMB's spectrum with a precision of 1 part in a billion, turning what's now theoretical into measurable reality. Critics argue that even if distortions exist, they might have mundane explanations: interstellar dust, galactic emissions, or subtle instrumental effects. But proponents counter that the shape of these distortions would be telling. Dark matter decay, for instance, would leave a distinct spectral fingerprint unlike any known astrophysical process. And if the distortions align with predictions from theories like supersymmetry, it could finally crack open the enigma of dark matter's identity. The stakes couldn't be higher. Spectral distortions might be the only direct evidence of phenomena that shaped the universe before the first stars flickered to life. They could reveal energy releases from cosmic strings, hypothetical defects in spacetime, or even the evaporation of primordial black holes. Every photon in the CMB carries a story, and spectral distortions are its hidden footnotes waiting to rewrite cosmic history. Until we measure them, the universe's oldest light keeps one last secret, the faintest echoes of its most violent childhood moments. The cosmic microwave background doesn't just tell us about light, it's also a silent witness to the ghostly particles that slipped through the early universe unnoticed. Neutrinos, those nearly massless, barely interacting particles, flooded the cosmos in uncountable numbers just seconds after the Big Bang. Today, they stream through your body by the trillions every second, leaving no trace. But the CMB remembers them. The way its temperature fluctuations are smeared across the sky betrays how many types of neutrinos existed in those early moments. And here's the puzzle. The math suggests there might be more varieties out there than we've ever detected. Standard particle physics tells us there are 3 types of neutrinos: electron, muon, and tau, each with their own antimatter counterparts. Yet when cosmologists analyze the CMB's precise patterns, the data subtly hints at the possibility of a 4th kind, dubbed the sterile neutrino. Unlike its shy but detectable cousins, this phantom particle would interact only through gravity, making it nearly impossible to catch in Earth-bound experiments. But if it exists, its presence in the early universe would have subtly altered how matter clumped together, leaving a faint but measurable imprint on the CMB's structure. The hunt for sterile neutrinos has turned into one of physics' most tantalizing chases. Laboratory experiments like Fermilab's mini booster neutrino experiment have reported anomalous results, brief flickers of extra neutrinos that disappear under closer scrutiny. These fleeting hints could be statistical noise, or they might be the first glimpses of something revolutionary. If sterile neutrinos are real, they wouldn't just add a new entry to the particle zoo. They could explain dark matter, bridge gaps in neutrino oscillation models, or even hint at extra dimensions. Yet the CMB isn't making it easy. Recent high-precision measurements from the Planck satellite show no strong evidence for extra neutrino types, tightening the screws on sterile neutrino theories. Some researchers argue this closes the case, while others counter that the CMB might simply be insensitive to certain sterile neutrino masses or interactions. The debate cuts to the core of how we understand the universe. Is cosmology the ultimate arbiter of particle physics, or are there puzzles too subtle for even the CMB to reveal? What makes this mystery so gripping isn't just the scientific stakes, it's the way it forces us to confront the limits of our tools. The CMB gives us a snapshot of the universe at 380,000 years old, but sterile neutrinos, if they exist, might have played their biggest role in the first seconds after the Big Bang, leaving only indirect traces. Future experiments like the upcoming CMB Stage 4 project aim to push the precision further, searching for minute ripples that could confirm or refute these shadowy particles once and for all. Until then, the missing neutrinos remain a cosmic riddle, one that could either unlock new physics or remind us just how elusive the universe's deepest secrets can be. One of the most pressing mysteries in modern cosmology isn't just hidden in the cosmic microwave background, it's a disagreement so fundamental it threatens to upend our understanding of the universe's expansion. Meet the Hubble tension, a glaring mismatch between how fast the universe is growing when measured by the CMB versus what we see when we look at nearby galaxies. It's as if the cosmos itself can't decide on its own speed limit, leaving scientists grappling with the possibility that something crucial is missing from our cosmic playbook. The heart of the conflict lies in two very different ways of measuring the Hubble constant, the number that tells us how quickly the universe is stretching apart. When astronomers use the CMB as their guide, analyzing the subtle patterns imprinted by sound waves in the early universe, they arrive at an expansion rate of roughly 67 kilometers per second per megaparsec. But when they turn to nearby celestial landmarks like pulsating stars called cepheids or exploding supernova, the number jumps to around 73. That gap might seem small, but in the precise world of cosmology, it's a chasm. The odds of this discrepancy being a fluke, less than 1 in a million. So what's causing the rift? One camp argues for hidden errors in our measurements. Perhaps interstellar dust is distorting the light from supernova, or our understanding of cepheid stars isn't as airtight as we thought. But as observations grow more precise, these explanations crumble. The other, far more thrilling possibility is that the universe is playing by rules we haven't yet discovered. Maybe dark energy, the mysterious force accelerating cosmic expansion, isn't constant as we've assumed. It could be growing stronger over time or interacting with dark matter in ways that mimic a faster local expansion rate. Some theorists even propose wilder ideas, like an undiscovered particle that briefly flooded the early universe, tweaking the CMB's snapshot in ways we're only now detecting. The stakes couldn't be higher. If the Hubble tension is real, if the universe truly expands at different rates depending on where you look, it could mean our standard model of cosmology is incomplete. We might be standing at the edge of a revolution where dark energy is more complex than a mere cosmological constant, or where entirely new physics lurks in the cosmic shadows. Telescopes like the James Webb Space Telescope are now joining the hunt, scrutinizing cepheids and supernova with unprecedented clarity. Meanwhile, next-generation CMB experiments aim to refine the early universe's expansion signal down to a whisper. Whether this mystery fades with better data or deepens into a full-blown paradigm shift, one thing is certain: the Hubble tension isn't just a numbers game. It's a cosmic tug-of-war between the universe's past and present, forcing us to ask whether we've misunderstood the cosmos all along, or if it's been quietly hiding secrets in plain sight. When light from the cosmic microwave background travels across the universe to reach us, it doesn't always follow a straight path. The gravitational pull of massive objects, galaxies, black holes, and especially invisible clumps of dark matter, bends and warps this ancient light like a cosmic funhouse mirror. This effect, called gravitational lensing, imprints subtle distortions on the CMB, revealing the hidden scaffolding of the cosmos. But here's the twist. When scientists measure how much the CMB's light has been lensed, the signal is stronger than our best models predict. It's as if the universe is packing more gravitational punch than its visible ingredients can account for, and the discrepancy has researchers questioning whether we're missing something fundamental in our cosmic inventory. One leading explanation points to dark matter behaving in ways we didn't anticipate. Our standard models assume dark matter is cold, slow-moving and clumping into vast, smooth halos around galaxies. But what if it's not that simple? If dark matter particles interact with each other or decay over time, they could form smaller, denser clusters than we've predicted, amplifying the lensing effect. These invisible knots would act like magnifying glasses scattered across the cosmos, bending the CMB's light more sharply than expected. Alternatively, there might simply be more dark matter out there than we've accounted for, lurking in regions too diffuse to detect by other means. Then there's the more controversial possibility. Gravity itself might not work the way Einstein described on cosmic scales. Modified gravity theories like MOND propose that the force weakens differently over vast distances, potentially explaining the extra lensing without invoking unseen matter. But these theories struggle to match other observations, like the bullet cluster's clear separation of dark and visible matter. The lensing anomaly sits at a crossroads, requiring either a tweak to dark matter's rulebook or a rewrite of gravity's laws. Skeptics argue the discrepancy could be an illusion. Measuring CMB lensing involves untangling a web of signals from foreground galaxies to interstellar dust. If we've underestimated these contaminants, the extra lensing might just be noise in disguise. Yet even after accounting for these factors, the anomaly persists, nudging scientists toward a tantalizing conclusion. The universe's hidden architecture might be stranger than we imagined. Whether it's unseen matter, tweaked gravity, or something entirely new, the CMB's warped light is forcing us to rethink what shapes the cosmos and what's still hiding in the shadows. In the 1930s, physicist Paul Dirac made a startling prediction. Just as electric charges come in positive and negative varieties, magnetism should have its own fundamental unit, a single, isolated north or south pole called a magnetic monopole. These elusive particles, if they existed, would rewrite the textbooks, offering perfect symmetry in the laws of electromagnetism. Grand unified theories, which attempt to merge the forces of nature into one framework, enthusiastically embraced the idea, suggesting that monopoles should have been forged in the unimaginable heat of the early universe. Yet when scientists scour the cosmic microwave background for any trace of these magnetic ghosts, they find nothing. The silence is deafening and, for theorists, deeply troubling. The absence of monopoles in the CMB isn't just a minor oversight. It's a crisis for some of physics' most ambitious ideas. According to grand unified theories, the early universe should have been flooded with monopoles during the phase transitions that separated the fundamental forces. These particles would have been staggeringly heavy. A single monopole could outweigh a grain of sand, and so stable that they'd persist to this day. The math suggests we should be tripping over them, with monopoles outnumbering atoms in the cosmos. Instead, detectors buried deep underground cosmic ray observatories, and even the CMB's pristine snapshot all come up empty. It's as if the universe forgot to pack one of its most predicted relics. This glaring mismatch forced physicists to invent an escape hatch: cosmic inflation. The idea is that the universe's exponential expansion diluted monopoles to near invisibility, stretching space so rapidly that these particles were effectively lost in the cosmic vastness. Inflation saves the day, but at a cost. It pushes monopoles so far beyond our observational reach that we may never find them, turning Dirac's prediction into a tantalizing what if. Some researchers argue this is a cop-out, a way to keep grand unified theories alive despite contradictory evidence. Others counter that inflation's explanatory power is too valuable to discard, even if it makes monopoles virtually undetectable. But the plot thickens. In recent years, exotic materials called spin ices have allowed scientists to create synthetic monopoles in the lab, quasi-particles that behave like Dirac's hypothetical entities. While these aren't true fundamental monopoles, they've reignited the debate. If nature can mimic monopole-like behavior in condensed matter, could the real thing still be hiding in some unexplored corner of the cosmos? The CMB remains silent, but the hunt has expanded to bizarre new frontiers, from ancient mica crystals to the depths of neutron stars, where extreme conditions might preserve these magnetic oddities. The monopole mystery cuts to the heart of physics' greatest ambition, unifying the forces of nature. Their absence doesn't just challenge grand unified theories, it forces us to confront whether we're missing a fundamental truth about how the universe arranges its building blocks. Whether they're waiting to be found or forever exiled by inflation, magnetic monopoles remind us that even the oldest light in the sky can't reveal all of space's secrets. Some puzzles demand more than observation, they require us to rethink the very fabric of reality. Deep within the cosmic microwave background's flickering patterns lies a clue so subtle most eyes would glaze over: the hunt for non-Gaussianities. To the untrained observer, the CMB's temperature variations appear random, like static on an old television. But scientists know better. If the universe's birth was as chaotic as we think, these fluctuations should follow a statistical curve called a Gaussian distribution, a predictable bell shape where extreme highs and lows are rare and middling values dominate. Yet whisperings in the data suggest something's off. Tiny deviations from this curve, these non-Gaussian fingerprints, could be evidence of cosmic pandemonium in the universe's first moments. Collisions between bubble universes, space-time shaking cosmic strings, or inflation models wilder than we've dared to imagine. The search hinges on a simple but profound question: how truly random is the CMB? If inflation unfolded as a smooth, uniform process, the quantum jitters it amplified should produce Gaussian noise, mathematically pure randomness. But if the early universe seethed with exotic physics like fields interacting violently or dimensions crumpling, those scars could manifest as statistical anomalies. Imagine rolling a die thousands of times and noticing that sixes appear slightly more often than probability allows. That's the essence of non-Gaussianity, a whisper of loaded dice in the cosmic casino. Some of the most tantalizing culprits behind these anomalies are cosmic strings, hypothetical defects in spacetime thinner than a proton but stretching across the entire universe. These relics of a phase transition in the early cosmos would have writhed like invisible spaghetti, slicing through spacetime and leaving telltale kinks in the CMB's patterns. If detected, their non-Gaussian signatures would be a smoking gun for physics beyond the standard model. Then there's the possibility of multi-field inflation, where multiple quantum fields jostled for dominance during expansion, creating interference patterns in the primordial plasma. Each scenario leaves a distinct statistical fingerprint, a breadcrumb trail back to the universe's most frenzied era. The challenge is separating signal from noise. The Planck satellite's painstaking analysis initially hinted at non-Gaussianities, but the evidence faded like a mirage under closer scrutiny. Critics argue that foreground interference, dust, galaxies, even our own Milky Way's emissions could mimic these anomalies. Yet optimists point to future missions like the Simons Observatory, armed with detectors sensitive enough to spot deviations as faint as 1 part in 100,000. The stakes couldn't be higher. Confirmation would upend our understanding of inflation, while a definitive null result might force us to rethink whether the universe's birth was as quantumly chaotic as we've assumed. What makes this mystery so electrifying isn't just the technical hunt, it's the philosophical weight. Gaussian randomness implies a universe governed by serene, predictable laws. Non-Gaussianities, though, they're the graffiti tags of a more rebellious cosmos, one where the rules we hold dear might have been written in the chaos of creation. Whether they are hiding in the data or waiting beyond our current grasp, these statistical ghosts remind us that even the universe's oldest light has secrets left to tell, and some might require entirely new math to decode. The cosmic microwave background's temperature map is often described as a snapshot of the universe's fiery infancy, frozen in time, but zoom in and the plot thickens. While the large-scale fluctuations match predictions beautifully, something strange happens when scientists examine the tiniest ripples. These small-scale variations, the subtle wrinkles that should have seeded today's galaxy clusters, are curiously smoother than our models predict. It's as if someone took a cosmic iron to the fabric of space-time, pressing out the finest creases in the universe's oldest light. This missing roughness isn't just a minor detail. It's a potential crack in our understanding of dark matter, gravity, or even the very physics that govern the early cosmos. One of the leading suspects is dark matter's hidden complexity. The prevailing theory assumes dark matter is cold, slow-moving, inert, and clumping effortlessly under gravity's pull. But what if it's not so simple? If dark matter particles interacted with each other or with radiation in the early universe, even briefly, those collisions could have smoothed out the smallest density fluctuations like a spoon stirring cream into coffee. Imagine dark matter not as an invisible spectator but as an active participant, its subtle push and pull damping the primordial chaos. Some models suggest warm dark matter. Particles light enough to zip through space at near light speeds could explain the anomaly, their motion preventing the tiniest clumps from forming. Others propose that dark matter might carry a faint electric charge, allowing it to tangle with photons in ways we've yet to detect. Then there's the cosmic plasma itself. Before the CMB was released, the universe was a seething ocean of particles and light, constantly colliding and scattering. Theorists calculate how quickly sound waves should have traveled through this soup, dissipating energy and smoothing fluctuations. But what if something amplified that damping? Unknown particles like hypothetical dark photons could have siphoned energy from the plasma, while primordial magnetic fields might have tangled the plasma's motion, erasing fine-scale structure. Even the neutrino sea, that omnipresent flood of ghostly particles, could have played a role, their relentless motion acting like a cosmic sandpaper on spacetime's smallest imperfections. The implications ripple far beyond the early universe. If the CMB's smoothness stems from dark matter's hidden interactions, it could explain why some galaxies today appear eerily devoid of dark matter halos, or why simulations overpredict the number of dwarf galaxies orbiting the Milky Way. Alternatively, if the culprit is an unknown damping mechanism, we might need to revisit our models of how matter and radiation decoupled in the universe's first moments. Future telescopes like the CMB S4 Observatory aim to scrutinize these tiny scales with unprecedented precision, hunting for the faintest whispers of physics beyond our current grasp. What makes this mystery so compelling isn't just the scientific puzzle, it's the way it forces us to confront the limits of our cosmic maps. The CMB's large-scale patterns have long been hailed as a triumph of modern cosmology, but its small-scale smoothness whispers of unfinished business. Whether it's dark matter's secrets, exotic particles, or something entirely unforeseen, the universe's oldest light reminds us that even the tiniest details can hold the biggest surprises. The cosmic microwave background doesn't just illuminate the past, it holds cryptic clues about the universe's accelerating future. Woven into its vast, whisper-thin patterns is the shadow of dark energy, that enigmatic force pushing galaxies apart faster and faster. The CMB's large-scale structure acts like a cosmic speedometer, revealing how dark energy has shaped the universe's expansion over billions of years. When scientists compare the CMB's ancient snapshot to today's galaxy surveys, they uncover a bizarre mismatch. The universe isn't just expanding, it's doing so with a velocity that defies gravity's pull. Dark energy's fingerprints are everywhere in this data, yet its identity remains one of cosmology's most stubbornly guarded secrets. What makes the CMB such a powerful dark energy detector? It all comes down to geometry. The size of the CMB's temperature fluctuations, those subtle hot and cold spots, acts like a cosmic ruler, measuring the universe's curvature and expansion history. If dark energy had been stronger in the past, those fluctuations would appear stretched or compressed, like a photograph resized unevenly. Instead, the CMB reveals an eerie consistency. Dark energy seems to have lain dormant for billions of years before suddenly dominating the cosmic scene. It's as if the universe hit a hidden switch, flipping from deceleration to acceleration around 5 billion years ago. Why? No one knows. The leading explanation, Einstein's cosmological constant, suggests empty space itself harbors energy that drives expansion. But when theorists calculate how much energy there should be, the result is off by a jaw-dropping 120 orders of magnitude. That's not just wrong, it's the worst prediction in the history of physics. The CMB offers alternative routes to unraveling this mystery. One approach studies the integrated Sachs-Wolf effect, where dark energy's influence subtly alters the CMB's temperature as it travels through growing cosmic voids. Another probes the universe's clumpiness, how galaxies assemble into clusters over time. Dark energy suppresses this clustering, and the CMB provides the baseline to measure that suppression. Yet every clue seems to deepen the puzzle. Some models propose dark energy isn't constant at all but evolves dynamically, its strength waxing or waning with time. Others suggest it's an illusion born from our misunderstanding of gravity on cosmic scales. The most radical idea, dark energy, might be the first hint of a fifth fundamental force, one that only reveals itself across the unimaginable vastness between galaxies. What's striking isn't just the mystery, it's the urgency. Dark energy determines the universe's ultimate fate, a cold, empty rip, a cyclical rebound, or something stranger still. Future CMB experiments like CMB Stage 4 aim to map dark energy's influence with pixel-perfect precision, hunting for deviations from Einstein's model that could crack the case. Until then, the CMB's silent testimony stands as both a triumph and a taunt. We've decoded the universe's baby pictures, but the future it foretells remains written in shadows. The cosmic microwave background claims to hold a complete inventory of the universe's ordinary matter, the protons and neutrons that make up stars, planets, and us. According to the CMB's meticulous ledger, baryons should account for about 5% of the cosmos. But when astronomers tally up all the visible galaxies, gas, and dust, they come up short. Nearly half the universe's normal matter is missing. It's as if the cosmos misplaced an entire mountain of atoms, and the hunt for these phantom baryons has led scientists to some of the most elusive corners of space. Where could they be hiding? One promising suspect is the cosmic web, those vast, thread-like filaments of gas stretching between galaxies like invisible spider silk. These filaments, predicted by simulations but notoriously hard to observe, are thought to contain reservoirs of warm hot intergalactic medium, or WHIM. This gas isn't cold enough to glow like stars or hot enough to emit X-rays brightly. Instead, it lurks in a temperature sweet spot, detectable only by the faintest absorption lines in the light of distant quasars. Recent advances in ultraviolet and X-ray telescopes have finally begun spotting this elusive material, but the numbers still don't add up. The WHIM might be just one piece of a much larger puzzle. Then there's the possibility of baryons hiding in plain sight, disguised by their own diffuseness. Gas doesn't need to clump into galaxies to exist. It could be spread in such thin, uniform clouds that our instruments simply overlook it. Imagine searching for fog in a desert by looking only for water droplets large enough to reflect sunlight. You'd miss the mist entirely. Similarly, the universe's missing atoms might be floating in ultra-low density halos around galaxies or lingering in the voids between clusters, too sparse to cast a detectable shadow. Some theorists even suggest these baryons could be tied up in exotic forms, like quark nuggets or dark atoms, structures so strange they evade conventional detection. The implications ripple beyond bookkeeping. If baryons are scattered in ways we've yet to map, it could reshape our understanding of how galaxies form and evolve. These missing atoms are the raw material for stars, planets, and life itself. Their distribution dictates where and how cosmic structures grow. Future missions like the European Space Agency's Athena X-ray Observatory aim to probe deeper into the warm, hot intergalactic medium, while next-generation spectroscopic surveys could reveal baryons hiding in the universe's dimmest corners. Until then, the CMB's stubborn mismatch stands as a humbling reminder. Even the ordinary matter we think we know best can still slip through the cracks of our cosmic senses. The cosmic microwave background is often called the universe's oldest photograph, a frozen moment from nearly 14 billion years ago. But what if that photograph isn't static? Fringe theories occasionally surface suggesting the CMB might actually be shifting over time, its temperature fluctuations evolving in ways that defy our understanding of cosmology. At first glance, the idea seems preposterous. The CMB is the remnant of a single, universe-defining event, its patterns locked in place by the physics of the early cosmos. Yet a handful of researchers argue that certain anomalies, tiny deviations in temperature or polarization, could hint at something stranger, a cosmos where even the oldest light isn't quite as timeless as we think. Most mainstream scientists dismiss these claims outright. The CMB's extreme stability is one of its defining features, a cornerstone of modern cosmology. If its patterns were truly changing, it would imply something fundamentally unstable about the laws of physics themselves. Imagine a candle flame flickering unpredictably billions of years after it was lit. It's not just unlikely, it violates everything we know about thermodynamics and the uniformity of space. Observations from satellites like Planck and WMAP show no credible evidence of temporal variation. The fluctuations we see align perfectly with predictions based on the universe's initial conditions, with no drift over decades of monitoring. But here's where the fringe theories get creative. Some propose that dark energy's influence might not be constant, that its strength could fluctuate over cosmic timescales, subtly altering how the CMB's light is stretched as it travels across the universe. Others speculate about exotic physics, like a slow leakage of energy between dimensions, which could theoretically imprint changes on the CMB over billions of years. The wildest idea, that variations could be evidence of a cyclical universe where the CMB carries faint echoes of a pre-Big Bang era, its pattern slowly morphing as the cosmos resets itself. The biggest hurdle for these theories is sheer sensitivity. Detecting minute changes in the CMB would require instruments far more precise than anything we've built, capable of spotting shifts smaller than 1 part in a billion over human timescales. Current telescopes like Planck simply aren't designed for that kind of monitoring. Future missions, however, might change the game. Projects like the proposed CMB Stage 4 experiment aim to map the CMB's polarization with unprecedented detail, offering a baseline so exact that even the faintest temporal whispers could be spotted. For now, the scientific consensus remains firm. The CMB is a steadfast relic, unchanging over observable time. But history has taught us that cosmology thrives on surprises. From the unexpected acceleration of the universe to the enigma of dark matter, some of our biggest breakthroughs began as heresies. Whether time variations in the CMB are ever confirmed or remain a curiosity, their very possibility reminds us that the universe's oldest light still has the power to unsettle and inspire our quest to understand it. Beneath the cosmic microwave background's grand tapestry of temperature fluctuations lies a hint of something far stranger, an almost imperceptible fuzziness, a whisper of the universe's tiniest possible scales. This is the realm of quantum foam, the turbulent, frothy nature of spacetime itself at distances so small they defy imagination. The Planck length, a scale a trillion times smaller than an atom. According to quantum theory, at these infinitesimal dimensions, spacetime isn't smooth and continuous but churns with violent, spontaneous fluctuations. Tiny bubbles of energy flicker in and out of existence, warping the fabric of reality itself. If these fluctuations could leave imprints on the CMB, they'd be the ultimate cosmic fingerprints, evidence of physics operating at scales no instrument has ever probed. The challenge is staggering. Quantum foam's fluctuations are unimaginably brief, lasting mere fractions of a second and vanishingly small. For their effects to persist across the universe and imprint on the CMB, they'd need some mechanism to amplify their signal, like ripples in a pond growing into tidal waves. One tantalizing possibility lies in cosmic inflation. If the universe's exponential expansion stretched these quantum jitters to macroscopic scales, they might have frozen into the CMB's patterns as subtle, non-random noise, a faint static layered atop the primordial light. Imagine blowing up a microscopic grain of sand to the size of a mountain. Inflation could have done something similar to spacetime's quantum tremors, magnifying them just enough to leave traces we might one day decode. Yet, even if these imprints exist, spotting them is like listening for a single raindrop in a thunderstorm. Today's telescopes, for all their precision, lack the resolution to isolate Planck scale effects. The Planck satellite, for instance, mapped the CMB with angular resolutions of about 5 arcminutes, fine enough to study galaxy clusters, but laughably crude for quantum foam. To detect spacetime's granularity, we'd need instruments thousands of times sharper, capable of perceiving fluctuations at the level of micro-arcseconds. That's not just a technical hurdle, it's a fundamental one. Quantum foam's fluctuations might be so chaotic that they average out over the CMB's broad strokes, leaving no discernible pattern behind. Some theorists propose indirect approaches. If quantum foam alters how light travels across the cosmos, it might introduce subtle delays or scattering in high-energy photons from distant gamma-ray bursts. Others suggest that primordial black holes, hypothetical relics of the early universe, could carry signatures of quantum foam's structure, their formation mechanisms tied to spacetime's granularity. But these are long shots, and the CMB remains the most promising, if elusive, window into this quantum frontier. Future advancements like quantum gravity detectors or space-based interferometers might one day bridge the gap, turning speculation into testable science. What makes this mystery so electrifying isn't just the technical audacity, it's the philosophical weight. If the CMB hides evidence of quantum foam, it would mean that the universe's oldest light remembers its tiniest, most violent beginnings. We'd be glimpsing the moment when gravity and quantum mechanics, the two pillars of modern physics, finally shake hands. Until then, the quantum foam remains a ghost in the data, a reminder that some cosmic secrets are written not in the stars but in the spaces between them. The shape of the universe isn't just a philosophical question. It's written into the cosmic microwave background's very fabric, hidden in the geometry of its ancient light. Most models assume our cosmos is flat, an infinite sheet stretching endlessly in all directions. But what if it's not? What if the universe curves gently like a balloon or twists into a pretzel like Taurus, where traveling far enough in one direction would bring you back to where you started? These exotic topologies wouldn't just redefine our place in the cosmos, they'd leave ghostly echoes in the CMB's patterns, subtle repetitions or symmetries that could betray the universe's true form. The hunt for these fingerprints hinges on the idea of cosmic crystallography. If the universe is finite and wrapped in on itself, light from the Big Bang would have multiple paths to reach us like a hall of mirrors. Imagine standing in a room where every wall is a mirror. You'd see infinite reflections of yourself, each slightly fainter. Similarly, a closed universe could produce ghost images of the CMB's hot and cold spots, repeating at intervals tied to the cosmos's size and shape. Scientists have scoured the data for these telltale duplications, searching for matching circles or correlated patterns in opposite corners of the sky. So far, the results are inconclusive. The CMB appears blissfully random with no clear signs of repetition, but that doesn't mean the topology isn't there. It might just be hiding in plain sight. One reason these echoes are so elusive is scale. If the universe is curved, the radius of that curvature could be larger than the observable horizon, making any repetitions vanish beyond our line of sight. It's like trying to detect the Earth's roundness while standing in a vast, flat-looking prairie. The curvature only becomes obvious at distances too great to see. For a toroidal universe, the twists could be so vast that light hasn't had time to complete a full lap since the Big Bang, leaving no loops for us to spot. Even if the cosmos is knotted like a cosmic donut, we might simply lack the perspective to notice. Then there's the problem of foreground noise, the Milky Way's dust, galactic clusters, and even the CMB's own polarization signals can mask subtle topological imprints. Untangling these layers is like trying to hear a whispered conversation in a crowded room. The signal might be there, drowned out by cosmic static. Future telescopes, like the proposed CMB Stage 4 experiment, aim to cut through this noise with unprecedented sensitivity. But for now, the universe's shape remains an open question. The implications stretch beyond geometry. A closed universe could spell an eventual big crunch, where gravity wins out over expansion, pulling everything back into a singularity. A toroidal cosmos, on the other hand, might allow for perpetual rebirth, with each cycle leaving faint scars in the CMB's structure. Even if the evidence remains elusive, the search itself forces us to confront the limits of our cosmic vision. The CMB has already rewritten the story of the universe once. Who's to say it won't do so again, revealing a topology stranger than we've dared to imagine? The cosmic microwave background isn't just a relic of the past, it's a time capsule with an expiration date. As the universe continues its relentless expansion, this ancient glow faces a slow but inevitable transformation. Right now, the CMB bathes the cosmos in microwave light, a faint whisper at just 2.7 degrees above absolute zero. But over trillions of years, as space stretches ever outward, those microwaves will redshift into longer and longer wavelengths, fading first into radio waves, then into imperceptibly low frequencies. The universe's first light won't vanish entirely. It will become an echo so faint that future civilizations, if any still exist, might strain to detect it against the cosmic silence. This raises a profound question. Is the CMB destined to become an indecipherable fossil? For cosmologists, the answer might surprise you. Even as the light dims, its secrets could grow sharper. Imagine a future where advanced instruments, far beyond today's technology, analyze the CMB's polarization with atomic-scale precision. Hidden in those subtle twists could be evidence of gravitational waves from the universe's first moments, signals too faint for current telescopes, but potentially detectable with quantum sensors or space-based interferometers spanning entire solar systems. The very expansion that stretches the CMB's light could also stretch our ability to read its finer print, like magnifying a fading manuscript under ever stronger lenses. But there's a darker scenario. If dark energies grip titans, accelerating the universe toward a big rip, the CMB's fate grows more ominous. In this apocalyptic model, the fabric of space-time itself tears apart, shredding not just galaxies but atoms, leaving no structure to observe the CMB's final flickers. More haunting still is the possibility of heat death, a cold, exhausted universe where the CMB's temperature bleeds into the void, achieving equilibrium with the background of absolute zero. No hot spots, no cold spots, just a uniform, featureless graveyard of entropy. Yet even in these extremes, the CMB might have one last revelation to offer. Some theories suggest that in a cyclically rebounding universe, each new Big Bang could imprint traces of its predecessor onto the CMB of the next cycle. Future observers, armed with knowledge we can't yet fathom, might decode these nested patterns like cosmic tree rings, reading not just our universe's birth but those that came before. The CMB's ultimate fate, then, isn't just about fading light, it's about whether the universe leaves clues for its own autopsy, or if its oldest story slips silently into the dark. From the eerie cold spot to the unsettling axis of evil, from phantom baryons to quantum foams, whispers the cosmic microwave background isn't just a frozen echo of the Big Bang. It's a living puzzle box packed with 25 mysteries that defy our understanding of space, time, and reality itself. Every anomaly we've uncovered, missing lithium, phantom flows, lensing excesses, isn't just a gap in our knowledge. It's a signpost pointing toward discoveries we haven't even dreamed of yet. Think of the CMB as the universe's first love letter, written in a language we're still learning to read. Its patterns hold clues to dimensions beyond our own, to forces older than atoms, to a past, and perhaps a future we've only begun to glimpse. The same light that confirms so much of modern cosmology also whispers, you've barely scratched the surface. What shaped the primordial universe? Why does gravity seem to play by different rules on cosmic scales? Are we alone in this reality, or is our cosmos just one thread in an infinite multiverse? The answers aren't just hiding in distant galaxies or black holes, they're coded into the oldest light bathing Earth right now. This isn't science fiction. It's the cutting edge of human curiosity. Telescopes like CMB Stage 4 and the Simons Observatory are already being built to probe these enigmas with unprecedented precision. Maybe the next breakthrough will come from a grad student analyzing data in a lab, or an amateur astronomer spotting a pattern everyone else missed. That's the beauty of cosmic exploration. The universe doesn't care who solves its riddles, only that we keep asking questions. So here's the challenge to you, yes, you, staring at the screen right now. Which of these 25 mysteries keeps you up at night? Is it the haunting absence of magnetic monopoles, the universe's strange symmetry bias, or the chilling thought that our cosmos might be curved into a shape we can't yet see? Drop your theories in the comments below, because the next big idea might just come from this very conversation. And if you're hungry for more mind-bending journeys through space and time, hit that subscribe button. The universe isn't done surprising us yet, and neither are we.